Welcome. This is the fifth in the Big History 2020 series. In this particular talk, I'm going to look at the Big Bang. In the last talk, we have been talking about that the universe is expanding. If it is expanding now, then it must have started from a very small entity. So using extrapolation back in time, then we'll come up to a point where the universe will be at infinite density and at infinite temperature in a finite time in the past. Now, this is impossible. Infinity is only a mathematical concept. It cannot be used as a physical method. So that means at this point, the um, the theory that we use will not work, or in particular, the general relativity that is being used to describe the laws of physics in the universe. So this is a singularity, a gravitational singularity. We don't know much about it, but there's but at a very short time after this infinity, then we probably can say something about it. So what is this very short time that we will definitely know nothing about? And that's called the Planck Epoch. In order to understand this point, we need to go back to a little bit of quantum mechanics. In quantum mechanics, there is a principle called the Heisenberg uncertainty. This Heisenberg uncertainty say that when we are trying to measure some two quantities, for example, one is in energy, another one in time, then the error or the amount of things that we can measure in either of them, the accuracy, say energy, and accuracy in time, when we use that and multiply together, they must be greater than a certain number called a Planck's constant. Now, if we take this into extreme, then we will say, okay, at certain time, the time will have it will be indivisible. At certain points, then time, this is the smallest unit we can measure time to. So that's called the Planck Epoch. The first statement here, most scientists now believe that we live in a finite expanding universe. Now, for the part expanding, that's part we know. We already have established proof that it is expanding by the Hubble's law. So whether it's finite or not, that is where the scientists have to believe in. And looking at this expansion, looking back in time, so sometime in the future, sometime in the past, the universe haven't existed yet. The universe existed for a limited amount of time. Currently, we estimate that to be 13.7 billion years. That means the universe was created about 13.7 billion years ago, or started appearing at 30.7 billion years ago. But this estimate might change a little bit depending on the measurement of the Hubble's law. Now, Hubble's law itself have quite a number of error, which causes a lot of arguments. For example, one thing is what about the distance? The Hubble's law depends on measuring the distance between us and the star, and then from that we calculate. We know the velocity from Doppler effect, and therefore we can plot it into a graph. So how do we measure such a large distance? So these are difficult areas, and that's why Hubble's law still have quite a bit of error in it, and therefore the best estimate at the moment is about 13.7 billion years ago. So 13.7 billion, we take that number, okay, we just assume this is the number we are going to use in the rest of the course. So 13.7 billion years ago, the universe will start what we now call the Big Bang. Now, Big Bang itself is not a theory about the origin of the universe. Big Bang is only a description of what happened after the Big Bang. That's so the Big Bang theory should actually be said is the theory of the universe after the Big Bang, because we really don't know what happened and why there's such a Big Bang. So that's number one. Number two is the bang itself is not an explosion as we commonly understood. Here, the bang means the sudden increase in space. The universe started expanding. This is what we have observed, and today is still expanding. But that means at the beginning, the universe suddenly started to expand. So that is what we know as the Big Bang Theory. The Big Bang Theory starts from the point immediately after the first Planck Epoch and then proceed onward from there. So just reiterate, the Big Bang does not explain what initiated the universe. What came before the Big Bang, we don't know. We have no evidence to tell us anything about what happened before that, so we don't know. The other thing is we also don't know what is outside of the universe. Even if it is something called outside the universe, we don't know, because what we can do is what we can observe within this universe. So anything beyond that, science will only give you the answer that we don't know. So what happens before Big Bang? We don't know. What is outside the universe? We don't know. Is universe expanding into what? We don't know. So there are some things we don't know. But bear in mind that although we don't know this kind of answer to this kind of questions, it doesn't mean that we do not know a lot of other things. So let's see what we know. Okay. So another caveat, I suppose, is that this theory is still being developed, because at the very beginning, when the universe is so small, we will assume that it is governed by particle physics and quantum mechanics. As it expands into the current universe, the theory describing it will be the general theory of relativity. Now, these two theories, one is describing a very, very small, tiny space, another one is describing a very large space. The dimension in between them, we are talking about 10 to many, many, many zeros after it. So it is a very large scale, and therefore the theory we have at the moment cannot be unified up to now. So people are still working on this grand unification, how we can make this theory integrate with each other more understandably. How can we understand these two theories at the same time and then make them work together? That's still a ongoing process. Okay, so let's move from the zero, that means the moment the universe appears, to about 10 to the power minus 43 seconds. That's one Planck time. So this time is 0 point and then 43 zeros and then a 1. So this is a very, very short period of time. Very, very short period. In this very, very short period, the universe itself might be 10 to the power minus 35 meters. So today, everybody is talking about the coronavirus. The coronavirus have the size of about 70 nanometers. So that will be 70 times 10 to the power minus 9 meters. But we are talking about here the universe is so much smaller than the uh, than the virus we are experiencing today. And the temperature is also extremely hot, maybe up to 10 to the power 32 degrees C. Again, these are known as the Planck length and the Planck temperature, because these are the temperatures which is outside of our ability to measure. It is limited by the Heisenberg's uncertainty principle. Immediately after that, then we believe gravity started to appear. There are four fundamental forces. The four fundamental forces are gravity, which understood as the attraction between mass, or in relativity's term is space itself. Then we have the electromagnetic interactions, that is the magnetism, the electrostatic force, and so forth. And then inside our nucleus, in the atom, at the very center of the nucleus, there's another two forces. One is the strong nuclear force, another one is the weak nuclear force. For example, we have an atom with more than one proton. Let's say helium. Helium have two protons and two neutrons. That's the stable helium. We must remember that the two protons are both positive and they are so close together. So there must be a very large repulsion force between them. But they still stick together. So that means there is another very large force, even larger than the electromagnetic force between them, to hold them together to form the nucleus. So that is the strong nucleus force. The other one is the weak nuclear force. We can observe some radiation, which is called beta decay. Beta decay basically means a neutron emits an electron and changes itself into a proton. So that is a beta decay. So why that happen? Because the weak force may release the holding of the proton and electron together. So there are the four fundamental forces. We believe that within the first 10 to the power minus 36 seconds, gravity is already acting. We don't believe that gravity, we may not know whether gravity is acting in the first 10 to the power minus 43 seconds, but we believe that gravity is already present immediately after the Planck Epoch. Then, since the force separate out, another separation of the force is the strong nuclear force. The strong nuclear force becomes separate out from the other forces, and therefore it is now starting to function. As it's starting to function, it will start to hold things together, and the universe will undergo a very extremely rapid exponential expansion. Because once your strong nuclear force separate out, that means there's nothing holding the tiny universe together, and so the universe will expand. It will expand within a very small fraction of a second. Okay, it's 10 to the power minus 36 to 10 to the power minus 32. So a very, very small fraction of a second. It will expand at least 10 to the power 23 times to about the size of a grapefruit, about 10 centimeters. At this point, there will be a lot of high energy plasma particles, everything, and it is distributed across the whole universe. Then electroweak force started to separate out. As the strong nuclear force, which separates out, the universe expands. Now the weak electro force also separate out. releasing a large numbers of particles, the W, Z bosons, Higgs bosons, etc. Now, in particular, Higgs bosons is the fundamental particles which gives rise to mass. So with Higgs bosons available, that means energy can convert into mass and mass can convert back into energy. So there is a dynamic change between energy and mass and every other particles coming out all at the same time. From about 10 to the power minus 12 seconds to 10 to the power minus 6 seconds, a little bit higher, heavier particles and more the particles which we are now more familiar with, like quarks, electrons, neutrinos, etc., now appear in huge numbers. And at that time, the universe has already cooled to about 10 quadrillion degrees. All the four fundamental forces now is in their present form. Quarks and anti-quarks hit on each other and then destroy each other to produce energy, and energy come back and then produce more mass, more quarks and anti-quarks combine again. So there is an ongoing process of this happening in large quantity. Then we come to the Hadron Epoch. That's from about 10 to the power minus 6 seconds to about 1 second. Now the temperature has cooled to about 1 trillion degrees, and it's cool enough for quarks to form hadrons like protons and neutrons. The heavy particles is now being formed at this temperature. But this is still such a high temperature that neutrons and protons cannot hold together to form nucleus. There's just too much energy to make them fall apart as soon as they are formed. So this period is the time forming all these hadrons rather than forming nucleus. The formation of nucleus actually happens immediately afterwards. From about 1 second to 3 minutes during this period, the hadrons, the leptons, and the anti-leptons, everything else now started to form and become the mass of the universe. That means now all the energy remains as energy, but mass becomes mass. And among the mass, there's of course electrons, positrons, neutrons, protons, everything. So all these things are now starting to appear in the universe, and they are forming and destroying each other, destroying each other all the time. But now the electron and positron pairs almost balance out, but not exactly. From 3 minutes to 20 minutes, this is the time the universe gives us the real nucleus. The nucleus of different atoms are being formed during this period. In this period, we have neutrons, protons colliding with each other, neutron collisions, proton collisions, and so forth. So how these neutrons and protons all come together all depends on the probability and how they can hold to each other. And this is the period where the ratio of all the elements are determined. So during this very big period, from 3 minutes to about 20 minutes, the universe will produce mostly hydrogen with a little bit helium and very tiny bit of lithium and nothing else, almost nothing else. Some other heavier nuclei might still appear, but that will be very rare. So most of the universe now is hydrogen, helium, lithium, nuclei, plus all these electrons running around. So it is still too hot for the electrons to stick to the nucleus to form neutral atoms. So we now have a very hot plasma. At this time, the universe continued to cool, but it is filled with plasma. Now, plasma is described as the fourth state of matter. Now, the three state we commonly know is the solid state, the liquid state, and the gas state. But there is a fourth state which is much more common in the universe, but not as common on Earth. On Earth, we can have some plasma. For example, you light a match. The light from the match is a plasma. At such a hot temperature, the fuel will becomes loses electron and becomes a charged particles, and combined with oxygen, which at such temperature also loses electron, and to form the product of the combustion. As the product combustion is formed, it will leave the flame, and then the flame will eventually run out of fuel, while oxygen is penetrating into the plasma, forming the product. So a flame is a plasma. If you recall, a flame is opaque. That means you cannot see through a flame. The reason is that in the flame there is a lot of positive nuclei and a lot of negative electrons all forming together in the plasma. Therefore, for a photon, for a light will bounce on these charged nuclei and electrons and bounce to all different directions. That means light cannot pass through. Light is constantly being bounced off from each other. So the universe at this time will be opaque. It is not a transparent like the universe today. Because the universe is still too hot, the electrons is not being captured by the nucleus, and therefore it remains in a plasma state. Then, at around 24,000 to about 3,000 years, the universe temperatures dropped to about lower than 3,000 degrees, which is about the same temperature as the surface of our sun. The electrons are being captured by the nucleus to form atoms. So we will have hydrogen and hydrogen nucleus capturing one electron, helium nucleus capturing two electrons, and lithium nucleus capturing three electrons, etc. So at this period, then it will lock down the ratio of hydrogen, helium, and lithium. The ratio is about 37% are hydrogen and 25% are helium, with just tiny traces of lithium plus other tiny traces of other elements. But most elements is not formed. So we have one question here. Then, if the universe is just hydrogen, helium, and lithium, where does all the other elements come from? Where is the carbon, the oxygen, the nitrogen, etc. come from? So that will be part of this Big Bang theory, this cosmology. We are going to understand the eventual developments of the universe. So we will start our next talk at around 300,000 years after the Big Bang. So we will stop here. Now, what is significant at this point? At this point, the universe temperature falls to around 3,000 degrees. A lot of these electrons is captured and to form the atoms. At this stage, the ratio of hydrogen, helium, and lithium is fixed, so to speak. So here we have one verifiable evidence. We can observe our universe to see whether the ratio is correctly described as this 75% hydrogen, 25% helium, with a little bit of lithium everywhere. So this is something we can verify. We can look at our universe and try to find out whether this is true or not. Although on Earth here, we have mostly not hydrogen, not helium. They are very rare on Earth here, whereas we have more other elements like carbon, oxygen, nitrogen, etc. So we will need to explain how that come from a little bit later on. So far with this model, it offers an overview, a very comprehensive explanation in terms of the abundance of light elements. That means the hydrogen, helium, and so forth, and the large CMB. CMB is the focus of the next lesson. Okay, is called cosmic microwave background, and then the large scale structure and the Hubble's law. All these will become clearer as this course progresses. But all this theory depends on two major assumptions. Number one, physics is correct from the very beginning of the Big Bang until now. All the physics laws that we discovered should apply. If it doesn't apply at a certain stage in the universe, then we must adjust the physical laws for today, because we assume that physics is correct ever since the universe is formed. The second is, of course, the cosmological principle, that the universe is homogeneous and isotopic. So what does it mean by homogeneous? Homogeneous means smooth, okay? But of course, in physics, they deal with mathematics. It is a abstract definition in abstract algebra. But for laymen like us, we can just understand it as uniform or smooth. Isotopic refer to the uniformity in all directions. That means there's no one direction which is special. In every direction, you should see the same thing, the same uniform thing. So that is isotropic. So this large universe should view from Earth as universally true in all directions, and Earth is not at the center of the universe. So we will continue with the story next time. By the way, up to now, the first 5 lectures are lectures I gave and then recorded separately. So I am doing this without input from my audience at the moment. From the next lectures onward, it will be the live event, and that means when I'm delivering the content, people can ask questions in the chat, and I will respond to these questions while I'm delivering the content, and they will also be available on the YouTube channel. So please join me. Next time is 16 Tuesday at noon, 12 Australian Eastern Time. So on next Tuesday, 16th March 2020, at 12 noon Australian time, I will deliver the 6th lecture on Big History. Well, you're welcome to join me at that time, and the address for that lecture will be available on my normal channel, the main channel, not on the English channel, because I don't have sufficient subscriber yet, and therefore I cannot post a post in the community at the moment. So I have to post the announcement in my main channel. So if you want to find me in the main channel, just search for my name, Albert Ip. You should be able to find me. Thank you for listening, and look forward to seeing you next Tuesday.